because we model the cell with purely rectangular stuff. But what you see is that it's possible within a purely position sensor hypothesis to recover the SINE law without any force consideration, but just saying that, okay, when the statolites are close to the cell membranes, there is an interaction, and so it will, in the end, leads to a bias in the oxygen distribution. So that's the first results we obtain here. And maybe for the last 3 minutes, I will just finish by saying that so far it's very strange, because it seems that gravity does not play a role at all in gravity sensing, okay? Which is obviously not possible. I mean, if there is no gravity at all, you expect there will be no response. So where is gravity here? And actually, I've talked about the SINE law, but there is another very famous macroscopic law in gravity sensing, which is the dose response. Most of the time measured in microgravity conditions, saying that, okay, the response of a transient inclination delta for a time delta t is proportional to delta t and to the effective gravity. So here we recover the gravity. So why there are these two very different laws? I mean, for steady inclination, you have the SINE law independent of gravity, and here for transient inclination, you have this dose response law where gravity occurs. So a very naive idea is, okay, it's just that it takes some time for the statolites to reach their final positions, obviously. It takes some time. This is the avalanche time. So if you incline not long enough your cell, the statolites just don't have time to reach their final positions. And so it makes sense that the response then depends on the gravity, okay? Because it's just that the position of the statolites at that time is not the final position. So it depends on gravity. And so we wanted to test these very naive ideas too. So we built a kind of a setup where we can transiently incline the chutes, okay, for a given time. And we put this on the rotating table so that we can also change the intensity of gravity. And again, the result was a bit surprising, because we got a kind of dose law, which means that the response depends on the stimulation times. So for small stimulation times, the response is lower than for permanent stimuli. So there is a kind of a dose law, so we were very happy. But when we change gravity, again, the dose law is strictly the same. There was no here effective gravity here. So it means that it seems that there is a dose law, and the fact that there is a dose law means that there is a kind of memory process inside the transduction pathway. And Yasmin Meroz will talk much more about that later. But the thing here is that this memory process does not depend on gravity, and actually does not depend on the statolite avalanche time. Because here, this is the dynamics of a statolites compared to this law. And we see that actually this time scale of the memory process is about 15 minutes. And this is much larger than the time it takes for statolites to flow. Okay, so there is another time in the pathway that is not related to statolites. And that can be related to pin dynamics or to oxygen dynamics, but it's not related to statolite flow. And again, we have made a model where here this time is related to the pin localization within the same model. So I just conclude, yeah, this is just a cartoon, but I just don't want to talk about that. Just to conclude saying that, okay, statosite is a position sensor, not a stress sensor. The sensitivity of plants, the high sensitivity of plant to inclinations, comes from the agitation of the statolite pipes induced by the activity of the cytoskeleton. We have evidence of a memory process about 15 minutes in wheat coleoptiles. It can depend on the organs, obviously, which enable us, I've not shown this, but to build a model that unified in a single framework, both the observed response for steady and transient stimuli, all right? And in the end, we also build a simple model based on the position sensor hypothesis, where the statolites interact with the pin that recover both the SINE law and this memory process. And of course, all the perspectives are about the molecular basis of those observations. And I'm pretty sure Mio will talk about that just after. Thank you very much for your attention.
Thank you very much, Joel, for this very nice introduction into the physics of the molecular biology that you're going to see in the next talks. Are there questions for you? It worked before.
Yeah, thank you for a very thought-provoking talk. I've noticed that in one of your experiments, you were using different particle sizes, and they behaved in very different ways. Can you comment about the optimal size of maybe the statoliths? Is there an optimal size?
Yeah, absolutely. This is what I've tried to convey here in this slide. So yes, there is an optimal size, because actually, if you estimate the vertical jiggling of the particles, it depends both on what I call this apparent temperature, which is not necessarily the real temperature, but can be a cytoskeleton-induced temperature, and the weight of the particles. And in the weight, there is the size to the power 3, because the weight is the density times the volume. So it's really the size matter a lot, which means that small particles are highly agitated, and we are in these situations where you cannot detect gravity. And this is really what happens in bacteria. For instance, there is in this paper, they show that some statoliths, it's not statoliths, but some particles in bacteria were used later by fungi in order to detect gravity. But in fungi, those particles aggregate to form bigger particles and then sediments. But in bacteria, the very same materials, you cannot detect gravity, because bacteria are much smaller and they use much smaller particles. So we are in this situation when there is not at all any clue about where is the up and down, because agitation is too large, particles are too small. So there is an optimum given by this ratio here.
Yeah, the reason I ask is I remember some of my colleagues who work on plastid division mutants. They have plastids which are much larger, and so the statoliths are much larger, and there's no difference in their gravity sensing behavior.
Yeah, I would say that there is no difference if you incline at 90 degrees.
Yeah.
Because at 90 degrees, agitation, whatever you do, even with large particles, if I incline at 90 degrees a pile of sand, it will flow.
Yeah.
But for the sensing around the vertical, which is the natural, I would say, state of a plant, I mean, it always tries to maintain the vertical direction.
Yeah.
That's crucial. So it's maybe also take a message that it can be interesting to do experiments not only at 90 degrees, but maybe to probe around the verticals. For roots, for instance, I don't know if this has been
That's a
done.
very good point, and maybe we should all think about that. A 90-degree bend is a very unnatural act unless you pull the plant up and it lies on the surface.
Yeah. Thank you.
But to comment on this, I mean, the 90 degrees is also where you get the maximum response, so you get the maximum resolution of the process. So there are mutants. Well, first of all, I mean, it's known that sugar, which drives starch formation and changes starch granule formation, has a strong influence on gravity. So if you say that the statoliths are not influencing the gravity response, I can tell you that in my lab, we have done work with mutants that have various levels of starch, and also have different starch granule compositions, so large granules versus small granules. And there we see very big differences in the gravity. So how does that play a role? So I mean, how do the number of starch granules influence the response?
Yeah. So, well, for us, it was a bit, we have not changed the number of made this kind of manipulation, but again, maybe we can have a hints for this. Again, with this here, for instance, there is the mass, so there is the density. So density matter and will influence this number. I mean, the kind of agitation, but also in the model we wrote. So in this model where we said that, okay, the auxin flux will be influenced by all the little interaction here. So the pin distribution here is given by the interaction between the statolite and the cell membranes. Here, the number matters in the end in the model. And I didn't comment on this, but in order to fit this data, you have several parameter in the model, and one of those parameters is the statolite level. I mean, the amount of statolites in the cell, and this matter. Also, the geometry of the cell matter. I mean, it's a very crude model, so I'm not sure at all it represents something that is real, but at least it gives some constraint. I mean, what could be the minimum model, that could account for that? And here the number occurs. So it makes sense that changing the number of particles can change the response.
Okay, so thank you very much. I think we have to conclude this. Let's thank Joel again. It's very nice that I can replace Stefan, who has sedimented now onto the